this is where we stopped last time we saw each other's. And we had a very simple piece of code in Faust, which just implement a Sawtooth wave oscillator. And we can control the frequency of the Sawtooth wave oscillator using a horizontal slider. So if we run this, sorry, we can control the pitch and yeah, the frequency of the Sawtooth oscillator. So this is where we stopped last time we talked. And actually, last time we talked, just before we left, I think Hassan asked a question about how to control the gain of this synthesizer, and I think some people already left at that time, so I'm just going to do that again. So Hassan's question was, okay, so we can control the frequency of the oscillator, and so the pitch of the sound that we are generating, but how do we control the volume? How do we control the gain of what we are generating here? So for those of you who've never done signal processing before, on a computer in real time, the standard way of doing that kind of stuff is just to multiply something by a number between 0 and 1, you know, because basically Sawtooth here outputs samples which are between 1 and -1. So basically your audio signal is just a stream of numbers between 1 and -1. That's what happens inside the computer. And so if you want to change the gain, the volume of what you are producing, of the sound you are producing, all you can do is just multiply this by a number between 0 and 1. If you want to decrease the volume of the sound, right? If you want to increase it, then you will have to multiply your oscillator by a number greater than 1, right? Which is a very bad idea in that case here, and I'll explain why later. But so here, if I multiply Sawtooth by 0.5, I'm basically dividing the gain of the Sawtooth oscillator by 2. Okay, and so if we run the program, and if we change this value just in real time like this, you can see that it actually works. This is definitely changing the volume of the sound that we are producing. So we probably want to be able to control that in real time without having to change the value by hand of the program. So what we can do here is just create a variable as we did for the frequency. So we're going to call that variable G. And we're going to say for now that G is equal to 0.1. Okay, and so now we can multiply Sawtooth by G. Okay, and so now we just externalized the value that we are using to control the gain here of the process line. So now all we have to do is to create a new slider, and we have to give it a name, and we can call it gain, because this is going to be our gain slider. The first argument here, as you remember, I hope, is the default value. So here we're going to say that the default is 0.5, for example. The minimum is going to be 0. The maximum value is going to be 1. And the precision is going to be 0.01. And usually the precision for a gain control has to be fairly high. And you'll see why later. So 0.01 is a good value here. And so if I run the program here, now I can control the gain of my Sawtooth oscillator. Cool. So, okay, so at this point, we almost have something that could be used as a musical instrument, like a traditional musical instrument, meaning that we could just plug this to a keyboard, like a piano keyboard, and control the sound that we are generating here with the keyboard. However, there is only one little thing that is missing here for this to happen. So currently we can control the pitch, we can control the amplitude, but there is one parameter that we are missing here if we wanted to map this to a keyboard, like a piano keyboard, right? Can someone guess what this would be, basically? It's very stupid. So it's a very stupid question.
An envelope?
That's that's kind of a more sophisticated answer than what I
Polyphony, maybe?
expected. But basically, what we are missing here is the ability to start or stop the sound, basically, right? So to do this, we're gonna add a button, okay? And this button is gonna allow us to start audio or stop it, okay? So the way we're going to do this is also relatively straightforward. So we can create a new variable. We're going to call it T as for trigger. And we're going to say that T is equal to button. Okay, so we have a button. And we have to give a name to the button. And we're going to call it gate. Okay, so the button primitive in Faust has only one parameter, and it's name, you know. And so basically the way button works in Faust is that if you don't press it, it outputs 0, and if you press it, then it outputs 1. Okay, so all we have to do here is to multiply the results of this operation here by T. Okay, and so the reason why this works, you know, is because once again, button will output 1 if we press it. So if we multiply this whole operation here by 1, then we will get sound. And if we release the button, then the button will output 0. And so we're going to multiply this whole operation here by 0. And if we multiply something by 0, it's always equal to 0. Okay, so no sound. Great. So now if I run this again, I have a button, and I can now control the fact that sound is going to be on or off. Great. So believe it or not, but at this point in Faust, this object is ready to be used with a MIDI keyboard or any kind of keyboard. Okay, so I'm going to show you how to do that. So in the Faust web IDE here on the left panel, you have a field here which is called Polyvoices. Okay, and it says mono. If you give it a different value, say 16, for example, okay, then you tell the Faust web IDE that you want to make this program a polyphonic program. And polyphonic means that you can play multiple voices at the same time, okay? And so here what we say with 16 is that the maximum number of voices of polyphony is going to be 16, okay? So you can't have more than 16 voices at the same time, which is totally okay with that kind of program because we only have 10 fingers, and so 16 voices is more than enough. You know, like even if we were pressing all the keys that we could press on the keyboard with our fingers, you know, like one finger, one key, then it would work. Okay, cool. So then, okay, let me just because I have Zoom on the way, and it's kind of preventing me from doing what I want here. Okay, great, sorry. So here on the right side of the Faust web IDE, you have MIDI input. And in my case, it says not supported, and that's because I'm using Firefox, and Firefox doesn't have built-in MIDI support, okay? However, I can choose computer keyboard instead. Okay, and computer keyboard is the keyboard of your computer. It's not a MIDI keyboard, right? But it's your computer keyboard. Now, if I run the program again, okay, now you can see that something changed in the interface. It says voices and it says polyphonic. Okay, so for now, let's not care too much about that. And now, if I click in the interface, like anywhere in the interface, just so that I'm not editing the code. So just go in here, I click, okay? Then if I press a key on my keyboard, like the A key, then I get sound. Okay, so right now I'm pressing the A key on my computer, okay? The Z and X key allow you to shift octaves. So if you touch X, you go 1 octave up, and if you touch Z, you go 1 octave down. Okay, so if I touch X, now I'm 1 octave up. And if I press multiple keys at the same time, then I can actually play a chord because it is polyphonic. It is a polyphonic object now. So if you were using Google Chrome and you had a MIDI keyboard, like a USB MIDI keyboard connected to your computer, instead of using your computer keyboard here, you could use a MIDI keyboard. Okay, so this kind of feature is not really going to be used too much during this class because we're going to use the Teensy anyway. So and on the Teensy, we're not going to have to think too much about having MIDI support or not. So here I'm just showing you that this can be done basically. Okay, so this is kind of cool, because it means that you can pretty easily turn your laptop into musical instruments based on the code that you're going to write here. And of course, your computer keyboard is not necessarily as good as a MIDI keyboard, but like that's already kind of a digital musical instrument that you can have with that. Okay. So one very important thing to remember if you do this is that if you want to keep editing your Faust program here, and you don't want to control it with the MIDI keyboard or your computer keyboard anymore, you should go back to Polyvoices and put it back to mono. Because if you don't do that, it might create weird issues, and maybe things are not really going to work anymore, and you're going to wonder why it doesn't make any sound. And sometimes it's because you forgot to go back to mono, which was our initial state when we started the program. Okay, so now if I click on here, it still works. Okay. Do you have any questions so far? Okay, cool. So I'm going very slow for
we had one question actually in the chat that was how would you reverse the functionality of the button? Like, let's say you wanted the button to by default have things on but turn it off by pressing it.
That's a very good question. So you could just do math, and so all you'd have to do is to say that. So you could like put parentheses around t here and say 1 minus t. Okay. So now it's doing the opposite, right? And so basically what I'm doing here is that, once again, button outputs 0 if you don't press it. It outputs 1 if you press it. So if you do 1 minus 0, it's 1. And if you do 1 minus 1, it's 0. So we just, that's one way to do it. Yeah? Cool. All right. So before we continue with Faust, okay, I'm just putting things back to how they were here. So one very important feature of Faust is that you can export a Faust program to a lot of different things, and that's something that we're gonna extensively use as part of this class. So this is something really really important to understand. So Faust is not limited to be used in the web browser, because that would be kind of useless, and especially, like in the field of audio signal processing, people are kind of scared of web browsers because, like you get clicks, and it's not something that you want to use in a concert setting. Like, I mean, you don't, like, some people might try, and in most cases it's probably going to work, but like if you're a professional musician and you're doing that kind of stuff, you probably don't want to have your synth running in your web browser, because that's it is a web browser. It's cool because it works everywhere, it's platform independent, and so using web browsers have a lot of advantages, but like you're kind of playing with fire if you want to play a gig for 2 hours using your web browser. So in the Faust web ID here, you have this little truck which says export, okay? And it's this little icon here. It's the truck icon. So if you click on export, then you're gonna see different things. So okay, first one doesn't really matter. Then you have your file name. So the file name is the name of the file that you are editing. That's important because in some cases it might change the program you will generate. Okay, so here I'm gonna give it a more sexy name than Untitled, and I can call it, for example, I don't know, my Sawtooth. Okay. So my Sawtooth.dsp. Then you can choose the platform, and you can see that there are a lot of platforms available. In my case, I'm running a Linux laptop, so I could choose Linux. Okay, and then I can see that for Linux, I can export my Faust program to any of those architectures. So what we call architectures in Faust are basically targets that you can use to turn your Faust program into something else. So something which is more like a finished product than just your Faust program in the Faust web IDE. So okay, since most of you don't really know Linux, I'm just going to show OS X, which is Mac OS. Okay, and for Mac OS, I could export my Faust program is a core audio QT application. And what a core audio QT application is an application, like a standalone application. So it's like a dot app on a Mac, okay? And so if you open it, it's going to have an interface based on the Qt framework. Okay, and it's going to make sound through core audio, which is the audio driver on the Mac. Okay, so I can't really show you that here because I don't have a Mac, but there are many more options, and including the Teensy. And so as part of this class, we're going to export a lot to the Teensy. Okay, and I'm not going to do that now because some of you don't have the Teensy yet because it's part of your kit. But very often in this class, you're going to find yourself just going here, choosing Teensy, and exporting your Faust program as a Teensy object. Okay. So for the demo here, so please don't do that at the same time as me, like what I'm about to do here. Okay, that's very important, and I'm going to tell you why. But just to complete my demo, I'm going to choose Android. For Android, there are multiple options, and I'm going to choose Android, and I'm going to click on compile. Don't click on compile, please. And the reason why I'm asking you not to click on compile is because basically what I'm doing now is converting my Faust program into an Android application. So like a smartphone application for Android, and so it's basically compiling an Android app from scratch, and we're using a Google Cloud server to do this, but it has a limited power, and if all of you at the same time were to try to make an Android app from scratch, doing what I'm doing here, it would probably, well, it's probably not going to kill the server, but it's going to make it very, very, very slow. So that's why I'm saying that you shouldn't do that. Like for the Teensy, it doesn't really matter because the Teensy is very quick at being compiled. It probably compiles in like half a second. It takes a lot of time to compile it. Okay. So now I'm kind of stuck, and I need to wait for my Android app to be compiled. But meanwhile, do you have any questions while this is happening? I'm gonna look at the chat, which I see that Doug is answering all the questions. But any questions?
Is there an opportunity to kind of customize the UI in a more complicated way?
That's a good question. So I'd say yes or no. And the reason why I'm saying yes or no is because basically the way user interfaces are declared in Faust is completely abstract. So it means that when you say, I want to have a horizontal slider or I want to have a button, those are just completely abstract things, like that go in your Faust program and tell the architecture that you're using that you want a slider and a button. Okay, and then depending on how the architecture was implemented, saying like using Qt or Android or whatever, then like the UI is probably going to look different on different platforms, basically, like depending on how it was implemented. So what I'm saying is that basically the user interface you declare in Faust is abstract, and it's just a description of the interface that you want, basically, and it's not really Faust itself that actually builds the interface. It's the architecture. It's the Faust architecture that actually takes care of that. So if you want to have a more advanced interface than the one provided with Faust, like everything is completely open source. So so it means that if you try to compile this on your computer, you will get access to the source. And when I'm saying on your computer, it's like not on the server. So if you try to get your Android application, for example, on your computer and build it on your computer, not remotely, then you will get access to the source code of the Android app that you're trying to make, and then from there you can potentially hack the Java program to try to get a different interface. So I know that's kind of what you guys are going to do in Music 320C. Because basically in Music 320C, you're only going to use Faust to generate the DSP code, basically, not the interface. And the interface is going to be added later using Juice from scratch using C++. So that's why I said that, like, the answer was kind of yes and no, basically. So cool.
So,
All
Romain,
right. So now,
can I ask you a question quickly?
Sure. Yeah, of course.
You showed a bunch of platforms and architectures. Would you recommend to work on a Linux environment? Or, I mean, I normally have a Windows machine, but I also have a Linux for example, Jacktrip. Given a choice, how solid it is on Windows?
That's a good question. So in the framework of this class, I'd say that it doesn't really matter for what we're going to do in this class, because most of the things we're going to do are going to happen in the web browser. So it doesn't really matter if you use Windows or the Mac or Linux. On the other hand, if you're planning on using Faust to make different things than programming your Teensy, say, like what I was talking about, like, for example, making a plugin with Juice, then I don't know. I mean, it will always be easier to use Faust on Linux and on the Mac, because it's a Unix-based platform. And on Windows it works, it's fine, but right. It's just that most of the developer of Faust are Linux. Using the Mac and Linux.
Yeah, I like everything else. So
like everything else, And
thank you.
So like Windows is supported, but like I'd say that it's better to use Linux or the Mac. If you don't want to have too much troubles, basically. So
sounds good.
Okay, so now I have my Android application. So what do I do with my Android application? You see that I now have a download button, so I can download the Android application on my computer. But there is also a QR code, and you can actually do that part if you want, if you have an Android device which has a QR code reader. So this is my Android scanning the QR code on the screen of my computer using my Android phone, and this gives me a URL which I can download. And okay, so I just downloaded the app on my phone, and now I'm opening it, and now it's installing, and I click on open. I say allow. Okay, and so now you can see that I have an Android application which sort of has the same interface as the one on the Faust Web IDE. And if I press the gate button, it makes the same sound as the sound in the Faust Web IDE. So that's kind of cool. So that's basically what Faust does. Like Faust is not an end in itself. Like you don't just write Faust programs in the Faust Web IDE to run them in the Faust Web IDE. Like what you do with Faust is that you write something, you prototype it in the Faust Web IDE, and then you export it to the platform that you want. Okay. Cool. So there are many ways that this program that I have here can be improved, and it actually has a couple of issues, and I just want to show them to you. So to show those issues to you, I'm gonna get back to a sine wave. So Julie Herndon is gonna be very happy because we all know now that she likes sine waves, and so I'm gonna say os.osc, okay, and I'm just gonna rerun the program just to be sure it still works. Okay, so I get my sine wave, great. So by the way, you can replace the button here by a checkbox, and what's cool with checkboxes is that when you click on them, you get sound until you click on them once again. Okay, so it's just like a checkbox, like a toggle. Great. So what I wanted to show you here is that there are actually some issues with the program that I wrote here, and namely, so here's some sound, and if I change the value of gain very quickly, I'm not sure how well that renders on your side, but did you hear those little? Yeah. Okay, I can do it. I can do it again.
Sorry, Romain, you just froze for a second.
Great. Okay, so yeah, because someone it's kind of complicated. Basically, I'm on a I'm still in the countryside, and I am on my hotspot, and someone gave me a call, and when that happens, it freezes the internet. So that's kind of annoying. Once again. Yeah. Can you say yes or no? Yes.
Yeah, we can hear it.
Okay, great, perfect, thank you. So so basically, okay, so can someone guess what the problem is here? Like, why do I hear those little clicks?
The frequency is changing very suddenly rather than smoothly.
Yes. So it's basically, I'm not going to go into too many details about that because it's not really what we want to do in this class, but basically the problem is a control rates versus audio rates issue. So audio is running much faster in terms of sampling rates than your user interface, and so those little clicks that we hear happen because the sampling rates of your interface is much slower than the audio rates, and so it creates little steps in the signal, and so that's what we hear. And those little steps are discontinuities that are applied to the signal that we hear here through the multiply of G that we have in the final process line. Okay, so how can we solve this problem? I'm sure some of you know the answer.
Smooth.
Yes, there we go. So one way to solve this problem is to basically interpolate the value produced by the user interface. And for that, there are multiple options. Like we can simply, for example, draw lines between each sample. So every time there is a new value, we basically draw a line to go from say 0.28 to 0.31. Okay. And so so that's the multiple, that's like the simplest way to do this, but in Faust there is a slightly more sophisticated way to do this, which is to use the smooth function. And so the smooth function is not only drawing a line, but it's doing it exponentially, which means that in terms of perception, it works better. Okay, so let me show you how to do this. So so it's very straightforward. So in Faust, if you want to connect something to something, you use the colon symbol here. Okay, so here I'm saying that I'm going to connect this slider to something else after the colon symbol here. Okay, and this thing is going to be a function, and this function is the smooth function. Okay, so here what I'm saying is that I'm connecting slider, the gain slider here to my smooth function. And so now if I run the program again, you can see that I don't have those clicks anymore. And so this is something extremely important because when you make digital musical instruments, which is something that we're going to do a lot in this class, you're always going to encounter this problem. Whenever you have a parameter to control, it's always going to run slower than audio rates. You know, audio rates is super fast. Currently, it's 48,000 samples per second. Your teensy could probably sample like the sensors that you will plug to them at this speed, you know, like, but it would take almost all the resources. So you never want to have such a high sampling rate for a sensor or for an interface, you know. And so basically, whenever we're going to have parameters to control in a teensy program, in most cases, you're going to want to smooth them to make sure that you don't have those ugly discontinuities in the sound that you produce. Okay. And it's the same for the frequency. Like currently, if I move the frequency slider very quickly, you know, it's like, right? So so basically you hear all those discontinuities, and they come from the fact that the slider here is not outputting values at the same speed as my audio rate. Okay, so I could smooth my frequency slider as well, and you know, just using my colon and then si.smooth, and then run that again. Now makes way more sense, right? Okay. So what?
Can I ask you a question? Which kind of interpolation does it do? It's like simply adding more values or doing some kind of parabolic interpolation? What's going on there?
So smooth is really like the most basic interpolation that you can do in Faust, and it's basically just a low pass interpolation. So so basically,
Cool.
smooth is a first order low pass filter, and it's normalized. So actually, you can see it in the block diagram of the program. So so for example, if you go to the block diagram, you know, I just clicked on the diagram here, and then if you click on G, you have your gain slider connected to smooth. If I click on smooth, well, that's the algorithm for smooth, right? So basically, this is a one pole filter, right? And so there is a one delay, one sample delay here. It's implicit. We don't see it. It's not specified in the diagram, but it's there. You know, like so. So here we have our Z -1. Okay, and this is the pole of the filter. So currently the pole of the filter is 0.999. Okay, so it's very close to the unit circle. And so it acts as a low pass filter, and because we don't want to add energy to the system, we basically multiply the inputs to this filter by 1 minus by the pole -1, and then so it's basically the opposite of the pole here. Okay, and so that normalizes the input signal and the output signal that we get here at the output of the filter. Does that make sense? Or
Yes, thank you so much.
sure. So and you can see that if you click outside of the block diagram, it allows you to go up, okay, in the hierarchy of the block diagram. Okay, so in fact, smooth is just some kind of syntactic sugar for another function in Faust, which is smooth. And smooth takes one argument, which is the pole of the low pass filter, and it's 0.999 here. Okay, so basically, si.smooth equals si.smooth 0.9999. Okay, and if you wanted to control the duration of the interpolation, because this pole is not very convenient for that, because we don't really know what it corresponds to. There's actually a function in Faust that you can use for that, which is called tau to pole. Okay, and tau to pole takes a duration in seconds as its input. So if you say 0.001, so that's like 1 millisecond interpolation, and it will convert this duration, which is in seconds, to a pole for your interpolation. So in music to 58, we're never really going to go that far. Like in most cases, we're going to be happy with smooth. There we go. More questions, or?
I have a question that I think might come up at some point here pretty soon, is how can you pass this output to stereo?
Yes, that is a very good question. So depending on the web browser that you are using, you might, and if you are using headphones, you might hear that there is only audio coming out on one channel for this program. Okay, so probably on your left ear. That also depends on the web browser, because in some cases, some web browser actually output. I'm not really sure why it does that, but in some cases you get audio on left and right. But for most people here, you probably only hear audio on the left side. So how do I make sure that I hear audio on the left and on the right? So, by definition, this algorithm that we wrote here only has one output. In Faust, the output that we get here gets automatically connected to the first thing that it finds, and for instance, it's going to be the left channel. Okay. So if I want to turn this into a stereo object, I need two outputs. And so how do I get two outputs out of this? Well, it's very straightforward. I can use the split operator. And the split operators takes one signal on one side, which is the signal that we have here. And then on the other side, it takes another set of signals. And so here I'm going to say underscore, comma, underscore. Okay, so what does that mean? Because I know this is kind of a weird syntax that many of you never saw before. But basically, what we're saying here is that we're taking the result of this operation and we are splitting it, into two signals in parallel. So in Faust, when you have an underscore, it means that it's just a blank signal. Okay, it's just a signal passing by. Okay, so it's a way for us to to specify a signal basically, and then we have this comma here, which just says that these two signals are in parallel. Okay, so if we wanted to have three signals, we could say comma underscore again, and now we have three output signals. And we could do 4, 5, 6, whatever, there is no limit to that. Okay. Except that currently my computer only has two speakers, and that's probably your case. So in your case, if you add more signals to this, the third signal is probably just going to be ignored by your computer, and it's just gonna go away somewhere. So only like the first two signals will be considered in this case. You know, and also in Music 250, we're not really gonna do like too much like multi-channel stuff. You know, like in the TNZ only has two outputs. You know, like so in most cases we're gonna be happy with just two signals like this. Okay. So now if I run the program again, well, if you guys are doing it as I'm doing it now, you can probably hear audio on your left and right here. Okay. So, okay, so since we are talking about this, let me show you another operator in Faust, which is the merge operator. So it's basically the opposite of the split operator. And the merge operator just looks like the split operator, but flipped 180 degrees. Okay, and so currently it's not happy. Like the Faust compiler is not happy because I didn't really specify anything after my merge operator. And so here I can just say that I'm gonna have one signal. Okay, so here I'm doing this weird thing where I'm taking the output of this operation here, and I'm splitting it into two signals, 1, 2. Okay, and then I'm merging it into one signal. Can someone tell me if this operation is passive or not? And by this, I mean, like, does this do anything, basically? Or is it like...
I think it'll be twice as loud.
Absolutely. So basically, you know, like if you were taking two electric cables, for example, okay, I'm going to say that this is one electric cable, this is another electric cable. You just split one electric signal into two cables, and then you merge those two cables again. You know, like what you get in the end is almost the same than what you had at the beginning of the cable, right? In Faust, that's not how things work. In Faust, when you use the split operator, you really just copy your input signal, so the signal that you have here twice. Okay, so here in underscore, we have a copy of OSC multiplied G multiplied by T, okay, and we have the same thing here, okay? So now we have two copies of the signal in parallel. And if we merge them together, then we basically add them together. So as David said, basically doing this corresponds to multiplying your signal by 2, okay? And if we were to add another signal here, so that we have 3 signals, then we multiply the signal by 3, etc., 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 okay? So this is very useless, but it's important to know about that kind of stuff, okay? Because when you're going to write more Faust code, you definitely need to know about those little details. Okay. Any other question? Or?
Is that equivalent to putting the gain to 2 or 3, depending on the situation? The split and the merge.
Yes, absolutely. So you know, yeah. So basically, well, I mean, it's a very bad way to do it. You probably never want to do it like this way, you know, like because it's kind of an ugly way, like from a syntactic standpoint. So once again, this is like multiplying by 3. So if I had to rewrite this in a different way, I could just say that. So by the way, this is how we comment things out in Faust. Okay, so / is a comment, and if you want to have a comment over multiple lines, it's just like in C++. You do /* and then */. Okay, and then everything that you have between those two things is considered as a comment. Okay. So here, what I wanted to show you is that basically this line is equivalent to this line here. Okay, so this is literally the same in Faust. Okay, if you want to multiply a signal by 3, it's way more practical to do it this way than this way, you know, like, but once again, you know, like, I think it's important that you guys keep that in mind, you know, that if you do that kind of stuff in Faust, then we'll multiply your signal by 3.
I have two questions. Just
Yeah.
to follow up on that, is there? It's the same thing, but on the diagram, it's not, because it splits into 3 on the diagram, and so just to clarify, is it? I mean, it's mathematically the same in terms of, like, you know, multiplying, but it's not the same, right? And then I guess my other question is, what about, like, when you're doing stereo things, like when you have, you know, multiple signals, but you're panning, or like you have like one thing on one channel, one thing on another. Like, is there a way that maybe you could show like a more complex example, and then like go through it or something? I think that would be really
Sure. So as you said, from a mathematical standpoint, writing this is the same as multiplying by 3. You know, like, so if you look at the C++ code, if you do this, or if you multiply it by 3, the C++ code will be exactly the same. You know, like, there is no difference between the two C++ code that you will get. So the block diagram, it looks different because you know, the way block diagrams are generated in Faust is just following the you know, Faust is programming language with a block diagram algebra. Okay, and so basically, when you use split or merge or underscore, comma, something, or, you know, like that kind of things, you basically draw a block diagram. Okay, so basically, the block diagram you get here is just a visualization of your Faust program, and so, like, from a mathematical standpoint, writing this or multiplying by 3 is the same. But in terms of block diagram, it's not exactly the same, right? Because in one case, you're just multiplying a signal by 3. And in another case, you're creating 3 copies of a signal and adding them together, which is basically the same as multiplying your signal by 3, right? So that's where the nuance is, basically. You know, I know it's a little bit hard to understand, you know, like at first, you know, like, but honestly, like, for Music 258, like, I don't think this is really going to be a very big deal. You know, like, I mean, you guys don't have to know too much about that. So that was to answer the first part of your question. Then the second part of your question. So how do we deal with stereo as independent channels, right? Because I think that was the sense of your question. And so, for example, how could we create a panner here, right? And a panner is just something that allows you to balance the amount of signal that you have on your left. So let's do it. I'm going to create a new variable, and I'm going to call it P for panner. Okay, and P is just going to be it's just going to be a slider. Okay, and the slider is going to have a name. I'm going to call it panner. And the default value is going to be 0.5. The minimum is going to be 0. The maximum is going to be 1. And I'm going to have panner is the same as my definition of gain. Okay. So now I have a slider which outputs a number between 0 and 1. And when I start the program, the slider is at 0.5. Okay, so how do I turn that into a panner in respect to the program that I have here? So what I want is that when panner is equal to 0, I hear sound on my left here, okay? So that things remain intuitive. And so in that case, I want P to be equal to 1, even though I'm on the left side. Okay, so I'm just going to multiply underscore by P minus 1, or sorry, 1 minus P. Sorry about that. And then for the other side, I'm just going to multiply underscore by P. Okay. And just to show you that this works, if I start the program, then I get signal here on the left, now signal here on the right. Okay. You guys probably don't hear it. But if you are trying this at the same time as I'm doing it, you probably hear that there's audio on the left and audio on the right, depending on the position of pattern. Okay. And so what I'm doing here, once again, it was just like some very, very simple math where I say that if P is equal to 0, which is the case when pattern is on the left side, okay, so currently P is equal to 0, then I have 1 minus P. 1 minus 0 is equal to 1, okay? So now I'm multiplying the left signal by 1, okay? And then on the other hand, on the other side, because P is equal to 0, I'm just multiplying the right signal by 0, so there is no audio, okay? Now when I'm at the middle, I get 1 minus 0.5 here, that's 0.5, and I still get 0.5 here, okay? So I get like the same amount of signal on the left and right here, etc. Does that answer your question, Hassan, or?
I mean, yeah, that makes sense. But I was just thinking, like when you have multiple like sounds, I'm just trying to figure out, like in Max, you can just like plug things in, and I'm more like I'm just trying to figure out how routing works, like for complex things. So if I have, like a simple example would be if I have like another sine sound, and I want to like process that a little differently than one. Like, can you have multiple processes, or is the process is your final thing, and then you need to figure out how to put everything in that one strand of code? I think if like there's like a complex example, you just like, or like it would, you could just be like, oh, this is how you do it. It's like, oh, okay. I don't yet wrap my head around that yet.
Yeah, so basically there is only one process line, okay, and so because there is only one process line, like the process line is like the very end of your program. That's like the top level of your program. So everything that you want to make sound in your program has to go in the process line, okay, or it has to be called one way or another by the process line, and like I mean. It's a programming language, it's not really just like Max, like where you can like write very horrible patches with wires everywhere, like that all go to the speaker. Here, like for example, like, and I'm trying to keep things relatively simple here so that everyone can follow, but I could create a function called synth, okay, and my synth could be like a combination of a sine wave oscillator with a certain, well, actually, I could use the frequency here. Okay, so my synth here is equal to os.osc. It could be a combination of a sine wave with a Sawtooth wave, and I'm using the frequency again, and also with a triangle wave. Okay, and here I'm using the frequency again. Okay, and now instead of using synth, instead of using OSC here, I can use my newly created synth. Okay, so now my program is a combination of a sine wave, a Sawtooth wave, and a triangle wave. Okay, it's probably going to click. It's probably going to click because I'm adding all these things together, and because I'm adding them together, the signal I'm generating is probably greater than 1 to minus 1, right? So so if I don't want this to click, I probably need to divide this whole thing here by 3 because there are 3 oscillators, okay? And sorry guys, for those of you who never done that kind of stuff before, like I'm just like showing this slightly more advanced. Now I have a combination of a Sawtooth wave, a triangle wave, and a sine wave, and clearly the Sawtooth wave dominates the timbre of the sound, you know, so it sounds like, but you know, it's just like for the sake of the example. So now if we look at the block diagram, we can see that the block diagram is the same, except that here we have synth, and synth is just OSC plus Sawtooth plus triangle, you know, like, and so basically on your synth line here, you could just like fit everything that you want, you know. Same for the process line. You could add more stuff on the process line, you know, like so. So does that answer your question, Hassan?
I think I'll ask afterwards, but basically, I'm just trying to figure out, like, say you want Sawtooth in the simple example would be like, say you want Sawtooth in the left side, say you want like a sine wave in the right side. So like just having them, but I'll figure. I'm sure I'll figure it out. I'll ask afterward. I don't want to derail it. Yeah, thanks.
Yeah, sure. Okay, so okay, let me do this last example, you know, like, because I think it's interesting, you know, like to study it anyway, like, but basically the way I could do this, you know, is just by so I can keep my panner, I can keep P here, and so what I'm gonna do is I'm gonna get rid of everything that I have here, and I'm gonna say that I have okay, let me actually do this a little bit smarter. I'm gonna say that process is equal to this. Sorry. That's okay. There we go. Sorry about that. Okay, so now I have my sine wave, my Sawtooth wave, and my triangle wave. Okay, so what I could do is that I could put them in parallel. Okay, so now I have Sawtooth, sine, so OSC going on the left channel. I have Sawtooth going on the right channel, and I have triangle going on the third channel. Okay, so now this is my block diagram. Okay, I have 3 signals, OSC, Sawtooth, and triangle, and they are in parallel of each other's, and that's what the comma operator is for. Okay, putting things in parallel. Cool. So now I can do like any operation I want on OSC, Sawtooth, and triangle, so that I hear them or not. You know, and currently, if I run the program, I get my sine wave on the left side, and again my Sawtooth wave on the right side. Okay, and then let me get rid of triangle here. Okay, and then if I were to reuse my panner function, I could do something like 1 minus p here, and then I could multiply this by p. Okay, and then if I run the program, I get a sine wave here and the triangle wave here. Does that help?
Yeah, that starts to that makes me start to see how this is functioning.
Okay,
thank you.
Good.
Sorry for derailing.
Perfect.
Thanks.
I mean, we can keep talking about it after class if you want. You know, like, I mean, I feel like we need to move on a little bit here, but I think it was a very good example to show anyway. You know, like, so that's it's good that you asked. Okay, cool. Okay, so let's move on a little bit here. So, okay, let me put things back to how they were before we started all this. So I'm just doing a lot of Control Z's here. Okay, great. So I think that's a good state. So if I run the program, okay, nice, perfect. So in sound synthesis, there is a concept which is very important, and that is kind of at the basis of everything that we do, which is the concept of envelope. Okay, and someone already mentioned that before. And an envelope is basically just the envelope that you apply to the amplitude of the sound that you generate. So currently, there is no, well, there is an envelope, but it's super abrupt. Okay, so let me put this back to a button. Okay. currently, if I click on gate, I get like, ta, you know, like it's very sharp. And when I stop sound, it's also very sharp, okay? What the envelope is basically just the shape of the curve you give to the gain of the sound when you start it and when you stop it. Okay. So a very, very, very simple way to create an envelope in Faust, and it's probably like the simplest way to do it, is just to apply a smooth function to your button. Okay, so here I'm gonna use smooth again. There we go. And because smooth is smoothing things up, basically, when I click on the button, you can hear now that basically I have a much smoother envelope on the sound that I'm producing. So when I click on gates, it's very, you know, like ooh, 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 right? As opposed to ta ta ta, right? So the envelope of a sound is really, really going to change the way it sounds, basically. And because different types of musical instruments have different types of envelopes. And so depending on if you're making a very percussive sound or if you're making something which is much like smoother, like from a perceptual standpoint, it's completely going to change the way you actually feel the sound, basically. Okay, so this is a very, very important parameter in sound synthesis. So smooth is super, super basic and not very controllable. But a way more standard way of implementing an envelope in sound synthesis is to use what do we call an ADSR or attack, decay, sustain, release. Okay, so if you go on the course website, there are links to that actually. But if you look for ADSR and if you look for an image, you will get an ADSR envelope. There we go. That's a very good example of an ADSR envelope. And so basically you get an attack, you get a decay, you get a sustain, and a release. And so in Faust, there's an ADSR envelope generator that you can use to apply this kind of envelope to the sound you will produce. Okay, so that's what I'm going to do here. So instead of using si.smooth, I'm just going to get rid of this here for now. Okay, and I'm going to create a new variable. I'm going to call it envelope. Okay, and I'm going to call the ADSR function. So by the way, in the Faust web IDE, if you hover the name of a function, it will give you a very brief description of the documentation of the function, basically. You know, like in here, you can see that ADSR, attack, decay, sustain, release, envelope generator. And you can see that ADSR has multiple parameters. There is the attack time, which is in seconds. You have the decay time, which is in seconds. You have the sustain level, which is between 0 and 1. And you have the release time, which is in second. And finally, the gates. So basically the trigger signal. So here I'm gonna say that the attack is, for example, 0.1. Okay, so that's 0.1 seconds. So that's 100 milliseconds. The decay is also 0.1. The sustain is, for example, 0.8. Okay, so back to this, right? This is basically the gain that we have here in function of the gain that we have here. Okay, so basically if you say 0.8, that's like a percentage of the maximum gain that you have here. Okay, and that's what I'm giving to the function here. Okay, and I'm going to say that we're going to have a very long release. And so I'm going to say that we have a release of 1, for example. Okay. And finally here, I'm just going to plug the T variable, which is my gate button. Okay. So now all I have to do is to get rid of T here and replace it by envelope. And if I click on gates, see? So now I have a much more complex envelope than the one I had with Smoo. And when I click, I have this very long release for 1 second, which clearly changes the way this whole thing sounds like, right? And I could use the Sawtooth wave to create another example. And changing the value completely changed the way you perceive the sound, and how it sounds in general. So here, if I put like a very long attack and a very short release, it will sound completely different again, right? So there's, like from a parameter space standpoint, we now have a fair amount of parameters to control in our synthesizer, right? Because we can control all sorts of parameters for the envelope of the sound that we are generating. And we can control the frequency, the gain, and the fact that sound is on or off. So we're starting to have a synthesizer with a couple of parameters that we can play with to change the sound that we are producing. So of course, if you make this polyphonic again, and your computer keyboard is selected here, you can still play this instrument, which is kind of cool. So let me close it and put it back to mono. Great. Any questions about the envelope generator that we are using here?
Sorry, this is something that everyone knows, but so the specific amounts that you're specifying there is are in seconds. Is that correct?
Yes.
Times.
So, yeah.
But so that means that, for example, for the first parameter, the attack, does it mean that it's going to take 1 second to reach the full gain that we have on the specified on the slider?
Yeah.
And that is a linear curve. It's not exponential, or do we have a choice?
We have the choice. So basically 1 second here is the time it takes to go. So basically ADSR here outputs a number between 0 and 1. Okay. So 1 second is the time it takes to go from 0 to 1. Okay. So if you say 1 second, it will take 1 second to go from 0 to 1. Okay. Then the next value is the time it takes to go from 1 to the sustained value. Okay, and the sustained value is 0.8. So here we say that it takes 0.1 second to go from 1 to 0.8. Okay, then
so sorry, just to understand, the 0.8 doesn't refer to a time. Is actually a gain.
Absolutely. So basically 0.8 is the gain of the sustain. Okay. And we always assume that the gain after the attack is 1. Well, unless we don't reach it, right? So if you release the button before you get to 1, then it will start the release immediately. And then we just forget about the sustain and even the decay, basically, right?
So the sustain will stay until we press the button again, basically.
Absolutely. So, or until we release the button. Okay. So here in the current scenario, when I start pressing the button, I go from 0 to 1. Then I go from 1 to 0.8 in 0.1 seconds. And then as long as I keep pressing the button, then I get a value which is 0.8. And when I release the button, then I go from 0.8 back to 0 in 0.1 second. Does that make sense?
Yes. And
Cool.
and is that a linear curve, or is that?
So currently it's a linear curve, but if you want to make it exponential, you just have to add an E here, and now it's exponential.
Great.
So,
got it.
it's just a different function, basically. And so now we have an exponential curve. Yeah. Cool.
Nice.
All right, so I think I'm going to stop for now, and I just want to talk about the lab and about the homework for the time we have left for today's class. Okay, so if we go on the course website, I'm sure you all checked that already, but basically all the stuff that we've been doing today and in the previous class were kind of what's in the lab. Okay, so I just thought that it's interesting to do it in real time. Okay, so if you go in labs, if you go in lab 1, Faust Basics and Digital Musical Instrument, I really strongly recommend you to just read all this and try all the examples. Okay, and like, unless you know Faust already, which I think is probably the case of some people here, I really strongly recommend you just like to read all this, just do it. It's not going to take a lot of time, but it's very, very good practice for what we've done, so part of it, we already did it in class, but I think it's good to, just read it anyway, so that it really solidifies the understanding you have of these things. Okay. So basically, we kind of stopped here. Okay, so we stopped at the envelope section here, okay, I didn't really read the lab as I was writing the examples, so they are probably slightly different than what we did, but then, yeah, please read everything until the end and try all the examples. There's more stuff on subtractive synthesis, how to use filters, how to do all sorts of things. So this is really your homework for this week. Just do the lab. Okay. Okay, you see that there are a fair amount of things, and we'll keep doing all this on Wednesday anyway. But then here you have assignment 0, discovering and playing around with Faust. It's due on April 7th, which is Wednesday, but there is nothing due. Like, once again, you don't have to. There is no deliverable for this lab, so it's a very abstract due date. Okay. And so that's what I'm saying here. There is no deliverable for the initial assignment. We just want you to get familiar with Faust and its programming environment by exploring the various resources which are at your disposal. Okay. Review all the steps of Lab 1. That's what I just talked about. By doing so, try to make some basic modifications to the example codes to solidify their understanding. Peruse the content of demos.lib, physmodels.lib, and of the Faust examples page. Okay, so just you'll know what this is if you read the lab. So we haven't talked about them so far, but please read the lab, and then you will know about demos.lib and physmodels.lib. Feel free to write test programs in the Faust Web IDE using some of the functions and examples that you'll discover. Have a look at the standard functions section of the Faust libraries documentation. Once again, I'm talking about all these things here, like the Faust libraries documentation. We haven't really talked about them during the class today, but this is part of the lab. So please read the lab. And finally, try to run the Faust 250A starter codes in the Faust Web IDE. So this is just a zip file. You download it. There are a bunch of Faust programs. You just take them, you copy and paste them in the Faust Web IDE, and you try to play with them, and you try to sort of understand what they're doing, basically. You don't have to get like a very deep understanding, but just read them, and try to see what's happening. Feel free to modify them. That's the best way to learn. Just look at the examples, try to make some very basic modifications to see what it does. So basically, this is just playing around with what we've done. One more thing that I want to say is that if you go in the lectures section, and if you go in audio processing in Faust, there are a bunch of hello, Karma, wake up. Okay, there are a bunch of resources that you should check. Okay, and I think I mentioned that in the email that I sent you, but there are the starter codes that I just talked about, the Faust website, the Faust Web IDE, the Faust Quick Start, which is just a tutorial. which really looks like what we did today, basically, and it's on the Faust website. There is the Faust manual, there is the Faust libraries documentation, there are Faust tutorials, there are Faust examples. And if you feel like you're really completely lost, and if you feel like you need more Faust in your life, you can also do the Faust Cadence course, which is free. And it's on the Cadence platform. It's a 10 hours class on Faust, and it's probably the most straightforward way to learn Faust. And the only problem with it is that I did it, and so if you're tired of my French accent by the end of the day, this is just even more French accent. So yeah, cool. Any questions? See, there are a lot of things happen in the chat. I always read the chat after the class, just so you know. Do we only have to read the first chapter? Yes. Do we only have to read the first chapter of Artful Design? Yes. Only the first chapter for now.
Oh, is it throughout the course or just for now?
No. There will be more. There will be more. It's just that for this week, it's the first chapter.
Oh, got it.
Yeah, good question. Yeah.
I have a really naive question, and I understand this isn't easily answerable, but I'm as someone who's like new to audio processing, like how do you get past the, like, I see that we're understanding the building blocks, right? There are these certain oscillations that we can produce easily with a computer, right? How do you, as an artist or a musician, how do you set like an aesthetic goal of like what you want the sound to sound like, and then hit that with the things that the code that you're writing? I know that's a very silly question, but how do you think about that?
It is a very hard question to, it's a very hard question to answer, you know, like, because unfortunately with audio DSP, there's like, unless you have a very constrained system, you know, like where you know, like you have a bunch of buttons and sliders and it's already working, and you're not writing something like from scratch, you know, then yeah, I see that Hassan is saying, yeah, really, that is the question. So then, you know, like there's rooms for you to explore, you know, like and as an artist, you can just like play around, you know, and maybe if there's a sound that you like, you know, like then you can try to look at the different parameters that you use, you know, and try to reproduce it. That being said, if you are writing your DSP just by yourself, without having much knowledge in you know, audio signal processing and sound synthesis, it's pretty tough to do what you're saying, you know, like being like, okay, I want this sound, and how do I write this sound for, you know, like how do I write the program to get this sound, you know, and the answer is the only way to do this is to know about audio DSP in depth, so that you can actually do it. And so you know, like it, because it's a very interesting question you're asking, you know, like they are in the history of computer music, there were different ways that people used to approach this problem, you know, and for example, in the French school, if we can call it like that, which is the IRCAM school, in a way, you know, like IRCAM is the brother of CCRMA in Paris. Okay, in the French school, there's always been people who are between researchers and composers, and those people are called computer music assistant. So if you're a composer, And if you go to EarCam and you want to write a piece and it's going to use like sound synthesis and stuff like that, then there is going to be someone who knows sound design super, super, super well, who's going to assist you in doing so, basically, right? And so that's one way that people found to solve this problem. You know, like in America, like people had a completely different approach to that. You know, like in this concept of computer music assistants is definitely less prominent. You know, like and I think a lot of artists think that they'd rather struggle with learning audio synthesis and DSP by themselves so that they don't get too influenced by an assistant who's going to tell them how to do something, basically, you know. And so so there is no simple answer to your question, basically, because like audio DSP and synthesis is a pretty hard thing to do. And unless you really know about the algorithms and the physics behind it, it's not something that you can just like do and program, basically. And it's always been a problem with what we do. So as for 258, we're going to try to not be too ambitious in terms of the sound that we are going to synthesize, you know, and we're really going to try to take this approach of simple is better. You know, simpler is better, meaning that maybe you're not necessarily going to have exactly the sound that you want, you know, like, but we're going to try to get you as close as possible so that you can reach your goals, basically, you know, like, but it is a very tough question to answer. And I see, yeah, please. Yeah, you are going to reply to what I said. But,
Oh no, yeah. Thanks for the answer. That makes a lot of sense. That's all I was going to say.
Cool. So you know they are in Faust and in other computer music languages. There are pre-written functions that already kind of implement instruments for you. You know, like so in Faust, you know, like if you read Lab 1, you'll see that there is, for example, a physical modeling library. And with the physical modeling library, the different instruments like a clarinet, saxophone, or whatever are implemented using physical models. And then you just have to use like the saxophone function to get a saxophone sound, you know, like, or something like that, you know, like, but so if you're not too picky about how things are going to sound like in the end, right, because maybe you're not going to like that saxophone sound, then you can use those functions, you know, like, but it's hard to do audio synthesis for sure. I see that there are a lot of things.
Do you have office hours today?
In the chat. So, sorry.
Do you have office hours today? Maybe later? Briefly, if possible.
So I actually, thanks for pointing that out, David. But so actually, Doug, did you decide on office hours or
I did, and
I was going to
office hours?
Or?
I was going to send out an email for them, but I can tentatively announce them, and if you know it doesn't fit for somebody, you can speak up now. Tentatively, I'm looking at 5:30 to 6:30 p.m. Tuesday, and that's Pacific time, and then 2 o'clock to 3 o'clock p.m. on Friday. Those were the times that seemed the clearest contenders for when people would be most available, and I checked as best I could, and there's nobody that's like fallen into a hole who couldn't do either, at least based on the responses I got in the poll.
Cool. And then as for me, I'm not going to have office hours today, but I was planning on having office hours on Tuesday evenings for you guys. So so I was actually thinking of Tuesdays at 6 p.m. for you. Would that be acceptable or?
Yes.
Great, thank you. Cool. I'll send out an email about that. But I'm just trying to follow what's happening on the chat. But there are actually a lot of questions. But I think there was a question about BLE MIDI, right?
Yeah, there was.
And what was the question? Because I kind of lost.
I'm just curious if Faust, if that, like, if you can send and receive BLE MIDI, or if that's even a question of Faust or of what you're compiling into, or.
So that's a good question. So like, you know, Faust is for DSP, so there is really nothing that will prevent you from using BLE MIDI with Faust, basically. You know, like, I mean, because Faust by itself, you know, like, is not really necessarily can you guys still hear me?
Mm-hmm.
Yeah, okay. Yeah, I wasn't really sure about that. Like, I thought everything froze. Sorry. So I don't think there is any Faust architecture currently which is implementing BLE MIDI, because, you know, like, those things depends on the architecture that you are using. So however, I think there is BLE MIDI support in Juice. Well, it's not I think, I'm pretty sure there is BLE MIDI support in Juice. So if you wanted to make an audio plugin using Faust and Juice, which is something which is fairly easy to do, then you could probably add BLE MIDI support to your plugin using Juice, basically. But by default, I don't think that there are many Faust architectures which are currently compatible with BLE MIDI. That you know, I'll try to get a better answer to your question, because that's that's kind of a tough question. But
Okay.
yeah, once again, I don't think that there are many architectures which are compatible with BLE MIDI. So